The second part of the problem asks us to find the thermal conductivity of the material. Our strategy to do that is going to be to look at this relationship that expresses the temperature change during the early stages when the heater is just switched on and the temperature is changing with respect to time. That is provided by this given equation. So let's just look at what we know so far. We know what the temperature is at 60 seconds. We know that that is 26.77 degrees. We know that the initial temperature was 23 degrees C. We can get the density because we know the mass and we know the dimensions of these disc-shaped samples. Mass divided by volume gives us mass per unit volume. We just have to remember that there's two discs. So we know these things. We know that this temperature is measured after 60 seconds. We also know this time. And we know the heat capacity from part A. We also know this energy input or the heat flux input. This is the energy input divided by the cross-sectional area. To get this Q double prime, we take the energy input by the heater, which was 20 watts, and divide that by the cross-sectional area. The total cross-sectional area, remember we have a top and bottom samples because the heater is sandwiched between them. Part of it's going through the cross-sectional area of the upper sample, and part of it's going through the cross-sectional area of the lower sample. So we have to multiply this by 2 to get the total heat flux, because the total area through which this 20 watts is being transmitted is the sum of these two top and bottom surface areas. With that in mind, then our only unknown is the thermal conductivity. So we can solve for that. And then as the final step, the problem asks to identify what material this could be. To do that, we can use tables A1 and A2 in the back of the book in the appendix. And we know now the material's density, its heat capacity, and its thermal conductivity. So we can look for a material that more or less matches these three parameters simultaneously.